had a smaller, there is a piece of paper over there. So we were giving us a small introduction, general introduction to the ocean. Now we will be looking into more specific features in the more specific subjects, which is the motion in the ocean and its dynamics. So we will be discussing the type of motion what we encounter in the ocean on one hand. On the other hand, we will be discussing the dynamics. So that means the forces which are generating this kind, the different kind of motions, and what are the features, characteristics of those motions. So we have to, as far as we have discussed with the heat and water balance, we have to look at the conservation laws leading to basic equations of fluid motions. So these are the conservation laws which are controlling or which are describing the motion in the ocean. One is the conservation of mass, which leads to the continuity equation. Conservation of mass means that there is no mass lost or gained in the entire ocean. Then we have a conservation of energy, which is, we already talked about that. This is the conservation of heat, which leads to heat budget. But the conservation of energy is not only the heat energy, it's also the kinetic energy. And then we have the conservation of mechanical energy, which leads to wave equations, so the wave solutions in the ocean. We have the conservation of momentum, which leads to momentum, which are the Navier-Stokes equation. Some of you already have heard about that. And then we have finally the conservation of angular momentum, which is very, very important since we are in a rotating system, and therefore angular momentum has to be conserved. And this conservation of angular momentum leads to conservation of vorticity, which we will be talking quite a lot later on. Which are forces in so that what is the dynamics of the motion in the ocean? So dominant forces are gravity, which gives rise to pressure gradient, buoyancy, and tides. Okay, so pressure gradient is a difference in pressure between different parts of the ocean. Buoyancy is the force which pushes the water upward in function of the difference of density. And tides, you know what are tides. Then we have the Coriolis Force, which results from motion in a rotating coordinate system, which is an apparent force which appears only in a rotating system like the Earth is. Then we have the friction. The friction is obviously the force which is due to the relative motion between different layers, or the difference in or the relative motion between air and the sea, which we already mentioned. That, for example, especially dramatic differences in the speed or in the relative motion between the air and the sea is where we have the order of magnitude largest speeds in the air with respect to that in the ocean. Then we have other forces. The atmospheric pressure. Atmospheric pressure presses the sea, so and results in an inverted barometer effect, what we call it. So that means that the higher is the atmospheric pressure, is lower in the sea level, and for each decibar of atmospheric pressor, the sea increase of atmospheric pressure for each decibar, the sea level decreases for 1 millimeter more or less. But this is the, and you will see also here, if you walk along the road, along the seashore, you will see that, for example, this type of weather, which is now, which you have the bora, this fresh cold wind, the atmospheric pressure is typically high, and being typically high, so that means that the sea level is pushed down, so the sea level is lower for this kind of situation. Or when you have the relatively warm weather and with the rain, so that means there is a low atmospheric pressure and the sea level is high. So this is partly influence of the atmospheric pressure, so this is the inverted barometer effect. Then we have seismic forces, which results in tsunamis and driven by earthquakes mainly, but not only. The seismic forces are something which causes large oscillations of the sea level, but they are very limited in time. While we have atmospheric pressure is an inverted barometer effect, which appears all the time. Tsunami appears only associated to the earthquake, and obviously you probably have heard that the tsunami has the different time scales with respect to, for example, to barometer effect. Tsunami has a typical time scale on the order of 10-20 minutes. But on the other hand, the oscillations of the sea level are rather huge. On the other hand, the inverted barometer effect or atmospheric forces influences have the time scale of several days. So these are the differences. But the amplitude of the inverted barometer effect is on the order of 10 centimeters, while the tsunami has the amplitude on the order of meters or 10 meters. And you probably heard for a number of tsunamis like this one in 2004, in 24 December 2004, when there was a strong earthquake in front of India, and there was a lot of human people killed. I don't know whether you have heard about that, or you were not born at the time. No. You were not born until 2004? How old are you?
Me?
Yes, for example.
So 21. 21.
21. So, no, you were born.
Yes, I was
But
6.
you don't remember.
Yeah.
Okay. You were too small.
Okay.
Yes. So, from that point of view, the last two forces are much less important than the first three. They are much less important in the sense that tsunami has this limited temporal scale, while the atmospheric pressure has a limited amplitude. So their influence is not so strong, so important as these first three forces, which are acting on a motion in the ocean in general. In function of the forces, there is also the characteristics of these motions, because these motions are they have a different temporal and spatial scale in function of the forces which are acting. So we have like a general circulation of the ocean, which is as its definition here is the permanent time average circulation, and this permanent time average circulation is due to the differences in temperature and salinity between different parts of the ocean, or in differences between the density between different parts of the ocean. And obviously these different parts of the ocean are responding to these differences on much longer time scales, on the order of a year or even thousands of years. Then we have the abyssal or deep circulation, which is circulation of mass in the meridional plane in the deep ocean driven by mixing. So this is also very slow process. First two are very slow processes and on a very long spatial and temporal scale. So they are covering the entire ocean. Okay. The wind recirculation is limited, obviously for obvious reasons, to a first kilometer of the water column, because this momentum, which is input by the wind, has decays with depth. Starts with the maximum, is obvious at the surface, and then decays with the depth. But in this case, the wind-driven circulation can have whole different time scales, all different spatial scales. Can be on the order of years, because to what extent the wind changes, to the same extent the circulation changes. But it can be also on the order of a day. So, and this, we will be talking about this later on. And this circulation can be can be generated by local wind, so that means by the wind which is blowing at this specific place, the current is there, responding there. So we have here, for example, today, Bora, the wind coming from northeast. And the response of the current to this specific wind here is the local response. But there can be also the situation in which the remote wind can force the current in this specific place. So there are two types of the response from the point of view of the wind. Then we have other features, other spatial scales of the circulation, like gyres. Gyres are the closed circulation features which can be generated by the wind. They are wind-driven and then can be cyclonic or anticyclonic, clockwise or anticyclonic, in function of what is the way, the sign of circulation. And then they can be on the order of a basin. So if you are talking about the Atlantic then or ocean, then they can be on the order of the dimensions of the ocean, so thousands of kilometers. Then we have the boundary currents, which are currents flowing along the coast and parallel to the coast. And we have two types of boundary currents. One is the western boundary current, and the other one is eastern boundary current. So it's currents, yes, that means that each ocean has this type of currency. We have western boundary current in the Atlantic, western boundary current in the Pacific. We have eastern boundary current in the Atlantic or in the Pacific. And western boundary current typically are very strong, and they are large, like on the order of 100 kilometers, so forth. And they flow from the equator to the poles. So they can go from Gulf of Mexico, for example, in Atlantic, or from Japan islands toward the northward along the western coast of Pacific or Atlantic. And or south, in the southern part, we have East Australian current, which is another western boundary current. And then on the other hand, we have eastern boundary currents, which are relatively weak, but on the other hand, they are very large. They are large on the order of 1,000 kilometers, because they are representing the return current with respect to this narrow boundary current which flows northward. The return current, eastern boundary current, is rather large, rather wide, but very slow motion. And then we have skirts and jets are long, narrow currents with dimensions of a few hundred kilometers that are nearly perpendicular to west coast. So they are kind of small-scale structures which are associated typically with the boundary currents. And finally, we have a mesoscale eddies. Mesoscale eddies, these are smaller closed structure with respect to gyres. Gyres are wind-driven cyclonic and anticyclonic features on the dimensions of the ocean, while gyres, eddies, mesoscale eddies, are smaller turbulent features which are closed, cyclonic again, or anticyclonic in function whether they are clockwise or anti-clockwise. And they have dimensions of a few hundreds of kilometers, and they move. They don't stay. They are not steady. They don't stay at a certain part of the ocean and stay there. They're moving since they are relatively small. They are moving back and forth. They are formed on the boundary currents, and then they travel in the ocean. And they have their lifetime. Their lifetime is on the order of a year or so. So they are born and they die. While the gyres are permanent structures which shows their variations, but they are always there because they are associated to steady winds. These mesoscale eddies are present not only in the ocean; they are present also in semi-enclosed seas, in smaller Mediterranean seas, but they are a smaller spatial scale. You cannot put in a Mediterranean or Adriatic. You can put the few hundred kilometers. Then they are on the order of 50 kilometers or so. But they are always mesoscale. They are equivalent. For you meteorologists, you know that they are equivalent to cyclones, to cyclones which appear in the ocean, in the atmosphere. Okay, mid-latitude cyclones, which are determining the weather in the atmosphere, they are equivalent to these mesoscale eddies in the ocean. And so in the atmosphere we call it weather. Weather is determined by mesoscale cyclones in the atmosphere, which travels in the northern hemisphere from west to east. They're bringing the rain and changing the weather, and they're called weather. Okay, but the same thing appears in the ocean, where we have these mesoscale eddies, and we call it sometimes weather in the ocean. Okay. So, why is this important? What is the first? Let's start first to look at the scale of the ocean and try to understand the steady circulation without considering the wind, without considering any forcing, except the differences in temperature and salinity. We call it thermohaline circulation. So the circulation which is caused by differences in temperature and salinity between different parts of the ocean, and also at the same time a difference in density, because temperature and salinity determines the density. And what is up here? What is determining the thermohaline circulation is the differential heating between the polar and equatorial areas. As we have seen also before, in equatorial areas we have prevalence of heating, solar heating, and then in polar areas, in polar regions, or starting from mid-latitude, we have the prevalence of the cooling. So here we have the heat gain, and here we have the heat loss. So if you look purely at the thermal circulation, so that means the differences in the different heating in the world ocean, looking in meridional direction, what is the result of that is that here we have the increase of temperature, and we have here a decrease of temperature. And what is happening here, since we have here the sea surface temperature decrease or cooling, the sea surface becomes colder than the deeper layers. Okay, because at the same time becoming colder, the density at the surface becomes higher than the deeper layers. This cannot stay for a long time, because the sea level, the seawater the water column cannot be unstable. Therefore, what is happening is that due to the fact that there is an increase of density in the surface layer, there is a sinking in a polar area due to the cooling in the surface layer. And this cooling then brings the surface water into the deeper layers, which then flows southward, but at the same time, since we have here the sinking, we have the loss of water mass in the surface. Having the loss of water mass in the surface, we have a difference of the sea level, but this cannot go forever. There should be a surface flow which compensates for this loss of volume in the surface due to the sinking. So we have the establishment of the surface flow northward. At the same time, in the deeper layers, we have a deep spreading of this dense water which is formed in the polar area. So we have, after sometimes we have the formation of the circulation north-south or polar equatorial area circulation cell. This circulation cell is closed and maintains the continuity of the water volume on one hand. On the other hand, redistributes the heat between the polar and equatorial areas, and so this is the pure thermal circulation. In fact, better to say thermal. It's a thermohaline. Why? Because there is another thing, what is happening, another process, what is happening here in the polar regions, is that there we have a cold and a continental wind blowing. So continental wind means that on one hand it's very cold, so it takes away the heat from the sea surface. But continental wind means that the air coming to the sea is dry. Being dry means that it takes very efficiently, the water causes very efficiently the evaporation from the sea surface. So we have two processes which are contributing to the increase of the density in the surface. One is cooling. So due to this cooling, due to the decrease of temperature, there is an increase of density. But on the other hand, we have also the increase of salinity, because there's an increase of evaporation due to the outbreaks of the cold continental air over the sea. So due to this combination of these two processes, we have the increase of salinity and decrease of temperature, and due to these two processes, we have acting in the same direction, we have an increase of density and very efficient vertical mixing. Therefore, that's why we have a thermohaline circulation, not a thermal circulation. this is one aspect of this thermohaline circulation. The other aspect of thermohaline circulation is that here in the polar area, the water column from the surface to the bottom is vertically mixed, because there is a vertical mixing due to this sinking of the water. And when we go from the polar areas toward the equator, there is a thermocline. Thermocline appears since there is no more vertical mixing over the entire water column. And you can see that the thermocline is closer to the surface in the polar areas and further from the surface in equatorial areas. And this is the permanent thermocline, what we were mentioning before and what we have seen from the experimental data. So most of these, this very simple scheme explains rather efficiently what has been seen from the experimental data. Just starting from a very simple concept of a thermohaline circulation, of the cooling in a surface layer and increased evaporation in the surface layer and the vertical mixing. So this is the thermohaline circulation, which explains, as I told you, rather well what is happening in a meridional transect across the ocean, north-south transect. As we have seen before from experimental data, this is what can be schematized along the north-south transect. But the situation is not really very simple if you look at a two-dimensional scheme. Two-dimensional scheme is this thing here, which is again very simple concept of the global circulation, of the global conveyor belt. We call it global conveyor belt as the global circulation in the world ocean due to this is the thermohaline circulation due to the heat losses in the polar areas. How it works? It works like this, and in the Atlantic extends further north than the Pacific. What is happening in the Atlantic in the northern part? In the northern part of the Atlantic, the sea surface heat losses are very efficient because Atlantic extends up to the northern pole almost. And there are strong winds blowing from the continent in that area, so causing the intense evaporation, intense cooling. And here in two places there are strong sinking of the sea surface waters, and here practically is the beginning of the thermohaline or global conveyor belt. So this water which is sinking here is spreading along the bottom of the ocean, Atlantic Ocean, then goes into the Pacific, into the Indian and Pacific Ocean. After some times, there is a very slow upwelling. So this water, which express in the bottom layer, slowly upwells, slowly wells up toward the surface, and finally, what it goes is this warm, less salty, shallow water current goes back and then compensates for this losses of heat, losses of water in this area here. So that's how we close this global conveyor belt. On one hand, we have the sinking in the Atlantic. Partly there is also the dense water formation or sinking along the Atlantic along the Antarctic coast, and the compensation for this loss of this, the sea surface or the surface volume of water is compensated by this warmless salty water countercurrent, which represents really the upwelled water from deeper layers, which came from this area here. So this is how it looks like this global conveyor belt. The one thing is also interesting, what one can put the question is, how much time does it take for a water particle which starts from here and does all this entire path and comes back? So this is what we call it residence time. What is the time needed to for the water particle, for the water to what is the memory of the ocean? The memory of the ocean in this specific case for this global conveyor belt is around 1,000 years. So 1,000 years is more or less the time scale which is needed for the water particle for the which sinks here, does all these path and comes back. This is the memory of the ocean. So if you put the signal, if you put the information right here for some information, whichever is this information, increase of higher temperature or lower salinity or higher salinity, whatever, it would take around 1,000 years that the entire ocean will feel this information, or will absorb this information. And this is something what has to be taken into account when we think also about the climate variability. If the decrease for some reasons, we will see later why the salinity here, the signal of the decrease of salinity will take like 1,000 years in order to be felt all over the world ocean. And so this is the how heat loss is the engine that drives the global conveyor belt. Heat engine, which is situated in the northern Atlantic, simply because of the fact that Atlantic is geographically open to the north, to the northern polar areas. Questions? No. This is how, this is the, we zoom to this, we zoom the conveyor belt to what is happening, for example, along the Atlantic coast. This is you recognize, this is the Florida coast, this is North America, this is Canada here, Europe is over there. This is the infrared image from the satellite, remotely sensed infrared image. So that means the sea surface temperature obtained from the satellite, and the more red, the reddish is more red the color is, the higher is the temperature. Or bluish, if you go to bluish, or then the colder is the water. The temperature is rather, this is Cuba, you can see here, Cuba, Florida. The temperature is very good parameter in order to understand or describe what is, this western boundary current, or how this northward flowing current, which brings the heat into the polar areas, behaves, because it has large temperature differences with respect to the surrounding adjacent water, because it brings the heat from the equator. In fact, what you see if you follow this red, strong red curve, you can see how this this flow goes along the coast of Florida, North America, then at a certain point detaches from North America coast around Cape Cod, and then flows toward the Europe. So what are the consequences of this thing? The consequences of this thing is that that here, this part here, is thanks to this high heat content due to this Gulf Stream, this coast up to here more or less has a rather mild climate, has a rather nice climate because the seawater is rather warm because it comes from the equator. Once it detaches from the coast, this becomes colder. So this part certainly here is colder that, not only because of the fact that it stays at the higher latitude, but also because of the fact that the current or the presence of the cold water adjacent to the coast. This is one thing. The other very interesting aspect is the temperature along the Europe coast. Where this Gulf Stream comes to the Europe, which is more or less the coast of England, there the climate is much milder than it is north of it, because of this. Also because of the fact that there is a Gulf Stream coming there. So, and this is one thing. The other thing is that you can see that this current is not really a simple river type of a flow. It's a very complicated structure with a certain number of closed features. You can see these closed features, and you can see also a number of meanders. We call it these meanders. You can see, which are then the places where the closed structures are formed. So it's a kind of instability which results then in the formation of these eddies. And these are these mesoscale eddies, what I was talking to you before a few minutes ago. These eddies then, they are formed along this current, and then they flow, they are formed here, and then they go into the center of the mid-Atlantic or Sargasso Sea, where they finally die down because of the friction. They cannot live forever. The friction destroys them, okay? And here is the schematic presentation of it. You can see that there is a southward current next to the coast, and then there is this Gulf Stream with these warm water. This is the warm water, this is the cold water, which is here, seen here. This bluish, this greenish thing is the cold water. These eddies, they trap the cold water and then flows toward the center of the basin. So we have these the cyclonic eddies, and you have these anticyclonic eddies on the left-hand side of the Gulf Stream. So this is how what is really the structure. What is really the real structure of this western boundary current, and how it looks like from a real remote sensing measurements. In the North Atlantic, so now let's zoom into the North Atlantic, where there is a dense water formation. This is the this is the Greenland, Labrador, and here is the area where the dense water is formed for the entire global conveyor belt. So the entire global conveyor belt depends on what's happening in that area here. If we, for some reasons, if we change the equilibrium here, if we add the heat there, or if we call different features, different characteristics of that area, we can block the entire global conveyor belt, which would have the terrible consequences for the entire climate of the ocean. And so what is happening here is that there is this circulation like this, and there is a flow. There are winds blowing from Greenland and Labrador, which are cold and dry, and they are causing the dense water formation or the vertical mixing in this Labrador Sea area. To give you an idea how big are these quantities of water which are keeping this huge amount of circulation flow, I can tell you that, for example, the North Atlantic Current or Gulf Stream has a flow of about 30 million meter cubic per second, around a few tens of meters cubic per second. So this is like 30-40 million meter cubic per second is the volume, total volume of water which flows by the Gulf Stream. Just to give you an idea of that, how big is this? The biggest river, which is, I think it's Amazon or whatever, has the discharge on the order of a few 100,000 meter cubic per second. So we have a 30 million with respect to the 300,000 meter cubic per second of river discharge. So this, you can have an idea how big is this, how important is how important is the water flow, for example, with a single component of this global conveyor belt, Gulf Stream, and you have to also consider that this water, which is like a 30 million meter cubic per second, brings the heat, the enormous quantity of heat from polar areas from equatorial areas to polar areas, contributing and changing and keeping the climate as it is now. Okay. So let's look at this process of dense water formation of the vertical mixing. How it looks like. What is the? Let's look at the description of this process. How it looks like and why it appears in a specific place and not in any other place, the dense water formation, because we can have, we do have the sea surface heat loss or strong evaporation in a number of places in the world ocean. But the dense water formation appears in a specific places, places which have a certain number of conditions satisfied. And so, what is here? This is the cross section. This is the cross section of the part of the water column, and these are the isopycnals. This thing here. These are the isopycnals. What you can see is the isopycnals are they are sloped in this way. They are sloped in this way, and they are at a certain point. This is the sea surface. They are at a certain point. They cross the sea surface. So what is happening is that here, in some places, there is a higher density of the seawater than the adjacent area. And what this helps to this is what we call a precondition. So the period when the seawater column prepares for the formation of the dense water, or for coming the cold wind. And when there is a cold wind coming, a cold and dry continental wind starts blowing, and there is a start of loss of the start of evaporation in the surface layer and loss of heat, because over this area there is a wind blowing, and due to this thing we have a loss of heat and loss of salt and increase of density, and this results in a upwelled isopycnals which are then crossing the sea surface, and so you have the formation of a kind of an eddy of a gyre at the surface, where the vertical mixing appears. So there is a vertical mixing over a very limited area, like we have seen in Labrador Sea, and which is the site of the dense water formation, or site of the vertical mixing. When the process continues, this is what is happening. It's happening that the eddy at the surface, this is the surface, the eddy at the surface limits the area where the water column is vertically mixed. It's vertically mixed because at this specific place, at this limited area, there was the dense water formation, losses of heat and losses of fresh water. So that's how it looks like. There are a number of things. Let's see how this looks like in real life in a circulation schematics showing the cyclonic circulation in the precondition of the Labrador Sea convection regime. So we have here the circulation this way. You will see later that the cyclonic circulation means that the isopycnals form a belt shape, and then this is the area where which is the area where the dense water can be formed due to the coming season where there is a strong cold and dry winds coming from continent. And so if you look at the vertical cross section, this is the vertical cross section across the Labrador Sea. What you can see is simply, this is the Labrador Sea, these are the area, and what you can see is that there is a huge area vertically mixed, where you can see that there is no isotherms from the surface up to 2,500 meters. The entire area is vertically mixed. No vertical gradient of temperature. Because no vertical gradient of temperature. Because there is a vertical mixing which mixes vertically the entire water column. The same is true for salinity. You remember when I show you the transect in the Adriatic where we are talking about the 50-meter depth and so forth. There, the vertical mixing was due simply to the wind influence. Here, it's not the wind influence which impacts this thing. Here is the loss of heat and the evaporation which causes this vertical mixing. And the same thing obviously in potential density. Potential density, you can see again up to 2,500 meters. There is the water column, the huge area. The water is vertically mixed. Where there was the sinking of the surface water into these depths, and then it's spreading along entering into the global conveyor belt. the importance of this vertical mixing is not only to drive the global conveyor belt. Obviously, this is the most important part. But the vertical mixing is also important because I might be mentioning to you before is that the sea surface water, which is rich in oxygen, because it is in contact with the atmosphere, is brought to deeper layers by this vertical mixing. So the ocean ventilates by this vertical mixing and brings the oxygen into the deeper layers to organisms which live there. So thanks to this vertical mixing, the deeper layers, the organisms in deeper layers can survive, can live. Not only bacteria, but all the other organisms which live there, which needs oxygen as we do. We do need oxygen. Without oxygen, we couldn't live. And the same thing is valid for the marine organisms. They can live only if there is oxygen, and oxygen comes from the atmosphere. By this vertical mixing. For shallower depth, by vertical mixing due to the wind influence. For deeper layers, due to this dense water formation, which appears in some specific areas. Okay. This is just to show the numerical model which shows this process. The dense water formation or vertical mixing appears as far as the relevant for the global conveyor belt appears mainly in Atlantic, and this is the main engine of the dense water of the global conveyor belt. But in some small Mediterranean or semi-enclosed seas, the dense water formation takes place as well, which is not important on a global scale, but it's important on a local scale. It's important in the sense that it's driving the thermohaline cell or conveyor belt of the semi-enclosed seas. So each semi-enclosed sea, if it's isolated from the adjacent ocean, has its own conveyor belt, has its own thermohaline circulation, and this is true also for the Mediterranean. Mediterranean has the conveyor belt, which is driven by two engines. One engine is in the Adriatic, and the other one is the Gulf of Lions. And just to give you an idea how it works and what are how we can understand this, which is the physical characteristics of the dense water formation are exactly the same here as in Labrador Sea, except that here is much easier to study this kind of things because of logistic reasons. Here you can see, for example, how the dense water formation appears in a specific year, in the winter of a specific year in the Southern Adriatic, which is the site of the dense water formation, is the same as Labrador Sea for the global conveyor belt. So what you can see is that there are four satellite images, but of chlorophyll data. Chlorophyll data is really the color of the sea surface or the phytoplankton biomass for the ocean. Why do we use the phytoplankton biomass as an indicator of the dense water formation? Because as I told you before, the dense water formation on one hand causes the vertical mixing. By causing the vertical mixing, brings from the surface to deeper layers brings the oxygen-rich surface water. But on the other hand, it brings from deeper layers into the surface nutrients. So the material which is then used by a living organism in the surface layer to live or to survive and to bloom. And these nutrients are used by phytoplankton because on the basis of that and oxygen, the phytoplankton blooms. And if you have enough nutrients, the phytoplankton blooms, and you can see it from the satellite. The color of the ocean reflects directly the concentration of the phytoplankton. Therefore, the color or the chlorophyll concentration of the surface, sea surface, can be used as the indicator of the dense water formation, because when you have the vertical mixing, you would have the phytoplankton bloom, and you would have a different color of the ocean. So we picked up the 4 subsequent satellite images. One is March 16, the other one is March 19, April 4, and April 15. So the distance between different images, satellite images, is on the order of 5 to 10 days. And you can see the dramatic changes between different satellite images. Just to give you an idea, the more red is the color, the higher is the concentration of the phytoplankton or the sediments. The more blue is the lower is the concentration of the phytoplankton. Okay, so the first image, which is here, what we can see here, we can see that the center of the southern Adriatic has a strong bluish color. So that means that the phytoplankton there is very poor in the biomass. Don't look at these things because this is the influence of the rivers, and so it's a sediment or phytoplankton, and they are not, doesn't depend on the vertical mixing. The vertical mixing appears here. If you have looked at this, here is a depth of about 1200 meters. If we have looked at in order to interpret these images, we have to look also at the satellite image, the atmospheric conditions. If we have the continental cold, dry air flowing over the ocean, so that means the wind blowing from the continent toward the ocean, then we would have the conditions favorable for the dense water formation. Okay? And what we have seen here is that, for example, in this first specific image, we have seen that there is a strong northeasterly wind. The wind blowing from the continent, cold, and what the result of that is that in the center we have the vertical mixing. But then you may ask, yeah, but it's vertical mixing, but why don't I have the high phytoplankton concentration then? Or even more than that, I have a low phytoplankton concentration. Why? I have a low phytoplankton concentration because I have a strong vertical mixing, and phytoplankton cannot stay for a longer time in the surface layer, which is rich in light. So the concentration of phytoplankton, even worse than it has a lower concentration in the center because of this vertical mixing, which doesn't allow phytoplankton to bloom, although the quantity of nutrients is very rich. If you go to the next, which is really, you can see it's like a negative picture of this one. Yeah? So where it used to be the minimum of phytoplankton, here is the maximum. Why so? It is so because here, respect this one to this one, here there is no more the northeasterly wind, no more wind blowing from the continent. And so what happens is that there is no more vertical mixing, which brings the phytoplankton from surface to very large large deep, very large part, very large deep part of the area, very large depth. And so phytoplankton has enough time to stay in the surface layer, being exposed to solar radiation and also having enough nutrients to bloom. Therefore, as a result of that, in this area where there was a vertical mixing, rich in nutrients, we have in a part of in a period when there is no strong wind forcing, we have the phytoplankton bloom. So phytoplankton bloom, or chlorophyll content, here is used as delimit the area where the dense water formation took place. And you can see that you see here, for example, this cyclonic circulation is perfectly seen here, except that the two are the negative image, like a negative image. You can see here another cyclonic feature, which is here. You can see here another cyclonic feature, which is here, and so forth. You can see perfectly delimited the dense water formation area by looking at the chlorophyll, concentration. Obviously, the phytoplankton, the surviving time of phytoplankton is on the order of a week or so. So you cannot see this. You have to be there at the right time, at the right moment. Otherwise, you wouldn't see this passage from here to there. And the phytoplankton would consume all the nutrients, and very soon it will start reducing its biomass, and you wouldn't see any strong signal associated with this. And indeed, like 10 days after, you can see that the signal is very weak. There is no such strong differences in phytoplankton concentration between the borders and the central dense water formation site. Some sign of this higher concentration still left. There is these vortices along the boundaries of the vertical dense water formation site, but the differences are smoothed down a lot. And finally, April 15, only 10 days later, there is no sign of the dense water formation at all. So you see how we can describe very nicely the process of the dense water formation and study picking up the right parameter, because if we took into consideration, for example, the sea level, we wouldn't see that. We have to pick the right parameter. The right parameter in this specific case is the phytoplankton or the chlorophyll concentration, in order to delimit this area where the dense water is formed. Just one more information, that the dimension of this patch of where the dense water is formed is on the order of 100 kilometers. So you have this 100 kilometer area where the dense water is formed during the winter time, during one event of the wind blowing over the area. This is the wind here. Now is the situation which can be good for the dense water formation, although the wind is relatively weak. We should wait for a much stronger wind in order to get the dense water formation event. And we have done the calculations of how much water is formed in this. Like we know in the Atlantic, this water which is formed there can be more or less equivalent to what is brought by Gulf Stream, that order of magnitude. we have done this calculation, how much the water is formed here, or how much of this water which is formed there flows into the adjacent sea, into the Ionian Sea. And we found out that the volume of this water which is formed is about 300,000 meter cubic per second. So 300,000 meter cubic per second. If you make an integral over the entire year, this is the total volume of water which is formed during these kind of events which look very, very limited in space and time. But they contribute to a large extent to drive this thermohaline cell, to drive the global or local conveyor belt. So, the if we go and see whether we do see this signal in the chlorophyll distribution on the monthly scale. So if you do the average monthly integral, the monthly integral of the chlorophyll distribution in the Mediterranean Sea, we should be able to see the signal of this dense water formation sites. And indeed, you can see that this relatively low chlorophyll concentration, which is associated in this part of the winter when there is a strong vertical mixing and low concentration of chlorophyll, is present in, for example, in February 99. And another place where the dense water is formed is the Gulf of Lions, which is here. And also here you can see the relatively low concentration of chlorophyll because of the strong vertical mixing in a specific month, in the month of February, when there is a strong the strong outbreaks of the continental air, or the strong outbreaks of the wind. If you look at the April situation, should be the situation when we should be able to see the signal of the higher concentration of the chlorophyll on the monthly scale. And you can see very strong signal on the high concentration of chlorophyll in the Gulf of Lions, which is the site of the dense water formation for the Western Mediterranean, which is this thing here. And you can see also for the Adriatic the same thing. So how these, so what is happening really is that the conveyor belt at the level of the Mediterranean is such that the dense water which is formed here flows through this channel, and then in a deeper layer flows all over the Eastern Mediterranean and drives local conveyor belt, the conveyor belt of the Mediterranean for the Eastern Mediterranean. The same thing is happening for the Western Mediterranean. You have here the dense water formation, which falls down into the deeper layer, then spreads around the Western Mediterranean, drives. So this specific site drives, or it's the engine of driving the conveyor belt of the Western Mediterranean. And this is exactly the analog of what we have seen in the global conveyor belt, except that here the time scale or the memory of the ocean, of the sea, which is much smaller, is on the order of 100 years. So the 100 year is the memory of the Mediterranean to whatever is happening. So if you put some signal here, it would take 100 years to be felt over the entire area of the Mediterranean. So this is the one order of magnitude smaller than in the world ocean. Obviously, if you go to summer, you don't see anything anymore because the chlorophyll, the signaling chlorophyll is not present anymore. Chlorophyll is at its minimum. There is no gradients in chlorophyll, and you can see that there is no such any differences between different parts of the ocean as far as the chlorophyll is concerned. You don't see any signal, no here, no here. The global conveyor belt is driven by the dense water formation site, so by this engine. The water exchange between a semi-enclosed basin and the ocean, adjacent ocean, is driven on due to the differences in temperature and salinity, or due to differences in density. And you can have two types of interaction between the ocean and semi-enclosed sea. So I'm just telling you this because the whole world ocean, the whole water all over the ocean is in a continuous movement. In the first part, due to the differences in temperature and salinity distribution. So you have a thermohaline forcing, which is important at the level of the world ocean, but also at the level of the water exchange between different basins. So, for example, if you have a basin where the evaporation is stronger than precipitation, you have a high density in a surface layer. So you have the density in the surface layer is higher, and you have the vertical mixing and the formation of the dense water in a semi-enclosed sea, which then across the strait outflows into the adjacent ocean in the bottom layer. So in the surface layer you have the inflowing the relatively fresh water, lower salinity water, while in deeper layers you have a higher density water which outflows. So we have this kind of circulation, and this is what we call where we have the evaporation higher than condensation basin, and we have evaporation stronger than precipitation. There are obviously, on the other hand, there are basins where the rain and river input is stronger than the evaporation. So it's more freshwater input into the ocean than the evaporation. In that case, the Mediterranean Sea gives the fresher water to the adjacent ocean, and as a compensation, you have the inflow of the dense water in the bottom layer and across the strait. So these are the two types of the ocean, of the adjacent basin, as far as the water exchange with the adjacent sea, the adjacent ocean. One of the examples of the water exchange of a condensation basin is the Mediterranean, where, as you remember, when we were looking at the distribution of salinity in the world ocean, we noticed that the Mediterranean has a higher salinity than most of the ocean. So the Mediterranean is the evaporation is larger than precipitation. So that means that the salinity, but also the density in the Mediterranean is higher than in the Atlantic. Therefore, what would happen? It would happen that the Mediterranean would exchange with the Atlantic, cross the Gibraltar Strait, which is a strait only 400 meters deep and around 40 kilometers wide, would exchange the water in the same in the way that the Mediterranean water would is outflowing in the bottom layer and inflowing in the surface layer. And in fact, this is how it looks like. These are from the real data, and this Atlantic Mediterranean water outflows sinks into the Mediterranean, into the Atlantic, and then once it reaches the equilibrium depth, which is around 1,000 meters in the Atlantic, it spreads horizontally. And this Mediterranean water can reach even the American coast at this 1,000 meter depth. You can see the signal of the higher salinity. On the other hand, obviously, you have the Atlantic water which enters the Mediterranean, and you can see these differences in salinity. This is 38.4, 38.0, the Mediterranean water, while the Atlantic water is 36 or 35.75. So these are the differences in salinity, which has been created by evaporation being stronger than precipitation. And this is the total water budget. You know, from the Atlantic we have 1.107 Sverdrup, because Sverdrup is a million meter cubic per second. So 1.1 million meter cubic per second enters the Mediterranean surface layer. Then we have a precipitation line which is about 27,000 meter cubic per second. And we have a river runoff which is 11,000 meter cubic per second. And this total inflow of the fresh water into the Mediterranean, including Atlantic precipitation and river runoff, is 1,152,000 meter cubic per second. And obviously this has to be equal one to another. And so the Mediterranean gives to the Atlantic 1,041,000 meter cubic per second. And then we have evaporation, which is 111,000 meter cubic per second. You can see that it is bigger than precipitation. So evaporation minus precipitation is positive, or evaporation is larger than precipitation. You can see that these two has to be equal, because otherwise there will be a continuous increase of the sea level or decrease of the sea level in the Mediterranean, which is not true. Just two more slides, and then we will finish. This is that's another cross section which shows a larger area, which shows how this Mediterranean water, in the form of tongue, spreads at the 1,000 meter depth toward the westward. And then you can see that this low salinity water of the Atlantic inflows the Mediterranean. This is again the cross section, but which is a larger area, so you can see how far away this can come. And this is the top view of this tongue of the Mediterranean water, which spreads southward, and you can see that it reaches this tongue reaches the coast of America or the Gulf of Mexico. Obviously, the salinity is not the same as at the origin, because due to the horizontal and vertical mixing, the salinity decreases, and these differences between the salinity of the Atlantic and the Mediterranean water becomes smaller and smaller. But nevertheless, the signal is still there. The presence of the Mediterranean water with all its characteristics is there, except obviously that these characteristics are not the differences in or contrast between within the characteristic of the Mediterranean water and the surrounding Atlantic water is much less expressed than it was at the very Gibraltar Strait. Okay, that's it. I will finish with this.